So thank you for introduction. And so I'm Takashi Imoto, so belonging to AIST from Japan. And so yeah, so I'm glad to be speaking at this conference and answer. And so I thank committee of INQA. And so yes, so this talk is based on so this archive paper, and so please check it if you are interested. And so this talk is collaborated with Susa, Yuki Susa, and Tadashi Kadowaki, and Ryoji Miyazaki, and Yuichiro Matsuzaki. Okay. Okay, so let's start. So first, so we discuss the result and the purpose of our talk, and so yeah, so my talk, so purpose of my work. So we propose an algorithm to perform the excited state search on the D-Web device, and so next we implement the excited state search using the D-Web device, and so. In this talk, so excited state search is an algorithm to obtain the excited states adiabatically, and so this excited state is does not mean maximally the highest excited state search is in this talk so excited state does not mean so the highest excited state. So we consider for example, first excited state or second excited state. And so finally, so we solved shortest vector program using quantum annealing with D-Web device. So that's a demonstration of our scheme. And so shortest vector program is one of the candidates for post-quantum cryptography. Okay, so let's overview the quantum annealing and the previous study related to it. Okay, so we introduced the quantum annealing. So first, we consider the annealing Hamiltonian as follows. So this one, and so HP denotes the program Hamiltonian, and so HD denotes drive Hamiltonian, and so. HP, so problem Hamiltonian is needs to be solved, and so HD has trivial ground states. Okay, and so quantum annealing, so conventional quantum annealing consists 3 steps. So first, so we prepare the ground state of the driver Hamiltonian. So next, so we perform the time evolution of T from 0 to capital T, so with this annealing Hamiltonian, and so capital T is called the annealing time. Okay, finally, so we obtain the ground state of program Hamiltonian, and so measure this state using the sigma z measurement. Okay, so and so it's not that it's nothing. Okay, so we should remark that when the annealing time to capital T is efficiently long, so we obtain the ground state with high precision. Okay, and so this is okay. Yeah, so this is this figure is concept of quantum annealing, and so white side represent drive Hamiltonian. And ground state of transverse field is the obverse state. On the other hand, left side represents problem Hamiltonian. Okay. Next, so we introduce excited state search in QA. So and this is the previous research. Okay, and so this excited state search is proposed by Seki et al. 2021, and so this is method for the so finding excited states of a problem Hamiltonian, and so we prepare the excited states of the derived Hamiltonian corresponding to the desired energy level as the initial state. And finally, so we need to resolve the degeneracy of transverse magnetic field. So thus we need to prepare the inhomogeneous transverse magnetic field as the derived Hamiltonian. So if we implement this protocol, so there is several problems in the dual device. Okay, so we need to prepare inhomogeneous transverse magnetic field, so as the derived Hamiltonian, and so we need to prepare the excited state as the initial state, and so there is difficult. Difficult to implement so in current dual device. Okay, so this is schematic diagram of excited state search, and so we can see that so the first excited state of the derived Hamiltonian is degenerated, so n-fold degenerated, and so by making the transverse field inhomogeneous, so this degeneracy can be solved. Okay, so next, so we introduce reverse quantum annealing, and so reverse quantum annealing. Reverse annealing Hamiltonian is given by this Hamiltonian, and so K knob T means scheduling function of reverse annealing Hamiltonian, and where K0 and K capital T equals 0, and so we remark that initial Hamiltonian and final Hamiltonian is become problem Hamiltonian. Okay, and so this protocol consists of 4 steps. Okay, so first, we prepare the candidate state as a potential ground state. Next, we add the problem Hamiltonian to transverse magnetic field, and next, we keep the state to stay for a while, and so finally. We reverse back to the problem Hamiltonian. So this is a scheduling function of reverse annealing. Okay, and so we should know that owing to noise and adiabatic transitions, we anticipate that some states will possess energy levels lower than that of the initially prepared state. Okay, so up to now, previous study, and okay, so here, this is our talk, our study, and so that's at first, we discussed the idea of the excited state search by using the D-Wave device, and yes, and the outline in our approach is follows. So first, introduce an inhomogeneous longitudinal magnetic field strong enough to make each excited state trivial for the problem Hamiltonian to be obtained. So next, we prepare the excited state of this Hamiltonian corresponding to desired energy level. And so next, we add the transverse magnetic field adiabatically. So it means slowly. And so next, we keep the value of the transverse magnetic field constant, and slowly set the longitudinal magnetic field to 0. So finally, so we rotate the transverse magnetic field to 0 and obtain the desired excited state. Okay. Okay, so in order to understand our scheme intuitively, so we prepare the schematic figure. Okay, so here, so we consider the problem Hamiltonian with longitudinal magnetic field, and so for example, the first excited state is trivial, and so here, so we consider the problem Hamiltonian with longitudinal magnetic field and transverse magnetic field, and so transverse magnetic field. So we keep transmagnetic field so constant, and so longitudinal magnetic field slowly decrease, and so here, so we consider the problem Hamiltonian and with transverse field. So finally, so we can obtain the excited state of problem Hamiltonian, and so we record this excited state of problem Hamiltonian is not trivial. Okay. Okay, so we should discuss how to choose the initial longitudinal magnetic field. Yeah, so let's consider the introducing longitudinal magnetic field such that electron make desired excited state trivial, and the problem Hamiltonian is given by this one, and so this is general two-body Ising model, for free connected case, and so next we consider generally homogeneous magnetic field, and so this is given by this one. Yes, so Hj is not uniform, and so thus this magnetic field is inhomogeneous, and so we should set HL as here this one. Okay. Okay, so next for each of the excited states of up to 2 power or 2k. So the energy gap is 2h. On the other hand, the energy of the Ising model E is satisfied as the inequality, so this one. Okay, so therefore, by configuring the longitudinal magnetic field HL to satisfy the inequality, so this one. And so the excited state of HL coincide with the excited state of HL plus HP. So yes, okay. So therefore, HL plus HP, the excited state of HP plus HL is trivial. Okay. So we should remark when utilizing the current device. A strong longitudinal magnetic field is essential. Okay, so next we should discuss what we can do with the device. So this is annealing Hamiltonian. So this is reverse annealing Hamiltonian, and so we can do with what we can do with the device, independent. We can implement independent control of longitudinal magnetic field and program Hamiltonian. So yeah, in other words, it means we can control the GK, this term. And so we can implement the control of the scheduling of conventional annealing Hamiltonian. So here, this one. And so finally, in the case of reverse annealing, prepare of arbitrary computational basis as the initial state. Okay. So on the other hand, So we cannot implement topic is so we can so independent control of transverse magnetic field and program Hamiltonian. Yeah, so in this Hamiltonian, so we can not so implement so independent control of so AK and BK, and so in addition, so we can not prepare so arbitrary initial state in so conventional quantum annealing. So this means so we cannot so prepare the so excited state of so transverse magnetic field. Okay, so this is so specific annealing Hamiltonian which we use in this talk. Yeah, so this is a scheduling function, and so HD is the transverse magnetic field, so HL is so inhomogeneous so longitudinal magnetic field. Yeah, okay, so then HP means so problem Hamiltonian. Yeah, so it is so too difficult, so too complicated to understand our so scheme. So let's show this so scheduling diagram. And so here, so at first, so when so t equals so time t equals so 0, so we consider the so problem Hamiltonian and so longitudinal magnetic field. And so next, so small t times t equals so t1. So we consider so problem Hamiltonian with longitudinal magnetic field with and so transverse magnetic field. And so next, so here, so we when so t equals so t1 plus t2, so we consider the problem Hamiltonian with transverse magnetic field, and finally, so here, so t times t equal to capital T, so we consider the only problem Hamiltonian, and so we can obtain so non-trivial excited state of problem Hamiltonian. Okay, so let's so introduce the demonstration of our scheme by using the dual device, and so this is the 2-qubit case. Okay, so we set so each Hamiltonian as so here. So HL means longitudinal magnetic field, and so this is so inhomogeneous. And so HP, so this is so ferromagnetic I think model, but so yeah, so this is only 2-qubit. Okay, and so set up. So we consider so upper state as initial state, and so this state is so second excited state of the problem Hamiltonian with so longitudinal magnetic field, and so answer state is up down and so down up. And so this is this state is so yeah, so second excited state of problem Hamiltonian, and so this state is degenerated, so twofold degenerated. Okay. Yeah. So just a moment. Okay. So this is so energy diagram of our scheme. And so here, this so right side when we consider the right side, so this is problem Hamiltonian energy spectrum. So on the other hand, so here, so the left side of this figure, so we consider the so problem Hamiltonian plus so longitudinal magnetic field. Okay, and so yeah, if we so our scheme to make it so yes, so so this energy diagram is this one. Sorry. Okay. Okay. So this is the result of our demonstration, and so this is the parameter which we use in this demonstration. Okay, and so so this here, so this green line is so up state, and so HD is more than so 0.8. So up state is the dominant, and so we should remark, so this state is initial state of our scheme. And on the other hand, so HD is so lower than so 0.6. So up state or so down state is dominant. So here. So this is so yeah. And so up and so down is ground state of the problem Hamiltonian. And so finally, so HD is more than 0.6 point, and so less than 0.8 regime. So down up is so dominant, and so this is the second excited state, and so success. Okay, so here. Okay, so let's interpret the result of our demonstration. Okay, so initial state is so why is the initial state dominant? So in weak transverse field regime. So here weak transverse field regime. So we consider so I think so non-commutability during the quantum annealing is so weak, and so change from the initial state is so very small. So thus so therefore initial state is dominant, and so this phenomena is called so freezing, and so we can interpret this phenomena as extremely strong non-adiabatic transition. Okay, so next, so on the other hand, we consider the so strong transverse field regime. So why is the quantitative dominant? Okay, so in DWAVE device, so the temperature of the environmental system is also very small and with so small number of qubits, and so we devise in the DWAVE device, environmental effects are so strong when the transverse field is strong. So yeah, so this fact is so referred to so next slide in detail. And so finally, so in strong transverse field regime, the ground state becomes dominant due to the effect of the environmental system. Okay, so we summarize so interpretation of the result of demonstration. So weak transverse, when we consider the weak transverse field, the initial state is the dominant caused by the freezing effect. And so when we consider the strong transverse field, the ground state is dominant from the environmental effect. Okay. And so this is the relaxation, it's energy relaxation time of the DWAVE device. And so we can see that when transverse field is large, so energy relaxation time is so small. And on the other hand, so transverse when transverse magnetic field is so small, so energy relaxation time becomes long. Okay, Okay, so this is a summarized slide. Okay, and so this is a 3D plot of our result of demonstration by using your device, and so this plot presented success probability against HD. So HD means the amplitude of transverse magnetic field, and 1 over T2. So T2 means yeah. So this time, okay. Okay. So we can see that success probability depends on not only the strength of the transverse magnetic field, but T2. Okay. Okay, so next, let's discuss application to shortest vector problem. So shortest vector problem is the basis for the difficulty of this diffusing lattice cryptography. So which is expected to be the candidate for post-quantum cryptography. And so this problem is attributed to the problem of finding the first exact state of Ising model. Okay, and so in detail, we explain the shortest vector problem. So for independent, L-dimensional basis vector, Bj, this one, and each integer coefficient alpha j. We define the vector v as this one. Yes, so v is linear combination of Bj such that coefficient alpha j must be integer. And this problem is finding a set of integer coefficients alpha j such that the magnitude of vector v is minimalized, except for zero vector. Okay, so this is schematic figure of the shortest vector program. And so this is it's too small, but this is basis 1, B1, so this is basis 2, B2, and V equals alpha 1, B1 plus alpha 2 plus B2, and this one, and so we can find, that program is finding the alpha 1 and alpha 2 such that V magnitude of vector V is minimalizing, except for zero vector. Okay, so next, we introduce the encoding from spin to multi-valued variable, and yeah, of course, there is several encodings from spin to multi-valued variable. For example, binary encoding or one-hot encoding, but we choose, in this talk we choose Hamming encoding, and this conversion is this one, and from binary to multiple variables. Okay, so left side hand, this one, this Qi means multiple variable. On the other hand, this one, sigma Pj, this is binary variable, and this is spin half, sigma z. Okay, and the shortest vector program reduced to the program of finding first excited state of the Ising Hamiltonian, as follows. This one. Yeah, this is the shortest vector program Hamiltonian, and yeah, in this Hamiltonian, so it includes so Qi and Qj, and so this is so we can convert so this operator to so spin operator by so this conversion. Okay, so therefore we yes, so okay, and so next, so there are so several approaches to so SVP, so shortest vector program by using QA. So first approach is using so adiabatic transition. Yeah, so this approach is so good point is so the web device can be applied. But the bad point is there is no guarantee that sufficiently long time will yield an answer with high accuracy. Okay, so therefore, for large systems, there is no guarantee that the extended annealing time will yield a correct solution with high accuracy. And so next approach is excited state search. But so in this case, so this excited state means the previous study. And so it is guaranteed that if we take enough time, long enough, so we will get a correct answer. So far, it has been difficult to realize by the web device. Okay. Okay, so this is so longitudinal magnetic field and problem Hamiltonian in so this so HP means so SVP Hamiltonian represented by the spin operator. Okay, and so this is the result of so demonstration of so SVP so thing shortest vector program, and so we can see that so here so AGD is more than so 0.8 so initial state is dominant, and so this is caused by so freezing effect. Then on the other hand, so here so HD is less than so 0.6, so one of the ground state is dominant, and so this is caused by the environmental effect. And so we choose HD, so transverse magnetic field HD is around so 0.6. So yeah, one of the answers, so down up, down down is so dominant. Okay, and so this is so 3D plot of our scheme, and yes, also we can see that so success probability depends on not only so HD transverse magnetic field amplitude, but also so T2 so annealing time. Okay, so it is summary. So we propose excited state search method using a web device. So with reverse annealing. And so we demonstrated our scheme in 2-qubit experimentally. And we need to bring an appropriate transverse magnetic field. And if the transverse field is weak, no change from the initial states occur due to freezing effect. And so if the transverse field is strong, the noise will cause a transition to the ground states. And so we demonstrate the application of our scheme to the shortest vector program in 4 qubits. And so we should remark, so we can control the scheme of the transverse magnetic field, and so program Hamiltonian individually. We can scheme is applicable to the large program with a strong longitudinal magnetic field. And so finally, so we so future work is so we should find the application for excited state search so in a variety situation. Okay, so it's over. So thank you for attention.
Okay, thank you very much, Imoto-san. We have time for questions. President Sorry.
Is there any prospect that this formulation of the shortest vector problem would lead to some form of quantum advantage? In other words, why do you study this problem in terms of quantum?
So you want to know quantum advantage is neat? What do you mean? So one more please.
Is this method of solving the shortest vector problem better than other classical or quantum algorithms in some sense?
So I don't know because we didn't compare with other classical approach, and and so this approach. So in this demonstration, so we can use only 4 qubits, and so this is a very small size, and so if we compare with what the classical approach, so we should implement the large size demonstration, but in current derivative device we can not implement it.
I ask this question because in the last part of your talk you said that you said that you are trying to apply this method to larger systems, and I wondered if you have any prospect to get good results.
Okay. Yes. Yeah, so just a minute. Yeah, so and I expect the quantum advantage of our scheme, but we didn't compare. So this one, and so this means that. So here, HP and HL, so we need to strong longitudinal magnetic field to make HL plus HL if HL trivial. But if we can consider if we can control the scheduling of HL and HP individually, here we can prepare the desired excited state initial state. So is it okay? So this is HP is amplitude of HP is
May I interrupt you a bit? I'm not asking a complicated question. You can ask yes or no.
Okay. I expect. Okay. Okay. Thank you very much.
Question from Kathy.
So I had a question about this slide. When you say possible versus impossible, are you talking about an engineering difficulty or something more fundamental? Could you ask the physicists of D-Wave to make it possible? Is sort of what I'm wondering.
It's very, thank you for good question. So it's very crucial point. But I don't know. So that point. So sorry.
Thank you.
I mean, my understanding is that in the D-Wave they have this coupling between the A and the B parameters.
I'm sorry?
In the D-Wave machine there's a coupling between the A and the B parameters that is a key part of the how it does the scaling. That's not necessarily the case. You could design squids that wouldn't do that.
I'm certainly not on the engineering staff, but I mean, you can prepare an arbitrary classical initial state. I'm thinking that's not what you want, but that's already part of the system. So I'm just curious. I know who to ask.
Okay.
Any other questions? Yes, in the front.
Thank you. Thank you for the talk. I just have a question about how do you choose the HL for the shortest vector problem, actually?
Yeah, so this one? No?
Yeah, how do you choose like the value of Hg? Because like in the 2-qubit example, I guess one was 2 and the other one was 1, while for the shortest vector problem, they were all 1/2. So how can one decide the value of HL? Is it problem dependent or?
Yeah. So it is program dependent, and so desired level of excited state is it depends. So we depend. So okay. So sorry. So it depends. So program Hamiltonian, and so desired level of excited state. So for example, so you want for first excited state or so second excited state, and so HL is so different. Okay, it's not.
Yeah. Okay. So like, do you have to know prior knowledge of the states of your problem Hamiltonian, right?
What do you mean?
I mean, like to compute like this H at the end of the day.
So H is this one. So this H.
I mean, the H of HL, the
H of
yeah. To compute them, like, do you need prior knowledge of the problem Hamiltonian?
Yeah.
Okay, thanks.
Okay, I think we should probably conclude there. So let's thank all this morning's speakers once again. Thank you very much, everyone.